Okay, now we have the information about the potential energy, and we talked about the spring and then the gravitational potential energy, and we have seen that the work done by the gravitational force would be negative work, and the work done by the uh, elastic uh, forces, the spring force, is a negative work done on the particle itself. Then we can rewrite the work energy equation in this open form. And in this open form, what we have here on the left hand side of the equation is the total work done on the particle. And this is from condition 1 to condition 2, or the initial case to the final case. And here we have the work done by the gravitational forces on the particle, it's a negative work, and the work done by the uh, elastic forces, and again it's a negative work. If we move these two terms onto the right hand side of this equality, at the end we end up with this new equation suggesting us that the work done by the forces other than the gravitational and elastic forces is equals to the change in the kinetic energy of the particle plus the change in the potential energy due to gravitational forces and the change in the potential energy due to the elastic force. So here we have a new equation that we can work out with. Now we just moved some of the external forces away from this definition, and these external forces that we moved away from this definition are the gravitational forces and external forces. The work done by all the other forces are listed underneath this U prime 1 to 2. As a matter of fact, in order to understand this concept completely, we need to take a look at the concept of conservative force fields. Work done by gravitational and spring forces depend only on the initial and final states, but not on the path followed. Remember, we had a similar case to this in here. For example, the particle moved on a path, but all that we were interested in was this h parameter here in the vertical direction, how much distance it has covered, right? It is a similar case for the spring here. For example, this particle attached to the spring will move from A to B, but all we're going to care about here is what was the extension at A and what was the extension of the spring at B, initial and final conditions. I don't really care about the path followed here. So for these type of forces, gravitational and spring forces, they depend on only initial and final states. The path followed doesn't really change anything. And since work done on these fields can be written as a change in the potential energy function, we call these forces conservative forces. So gravitational and elastic, or you can just call it spring forces, are conservative forces. All the other forces acting on the system, external forces I'm talking about, all these external forces acting on the particle are called non-conservative forces. So having that definition, now I can call this U prime 1 to 2 as the work done by the non-conservative forces, because the work done by the conservative forces are listed here as for the gravitational forces and here as for the elastic forces. Now, this example shows us the difficulty in doing this integration over a certain distance of spring forces. If we draw the free body diagram of this particle, you will see that there's this n reaction forces. So to keep this particle within this guide, there are the external forces F1 and F2. And you can imagine that this n will not do any work, by the way. If there's no friction here, if this slot is frictionless, this n will have no effect on the motion of this particle. And other than that, keeping it in the guide, other than that, we're not going to see its resemblance in the energy equations. But in any case, we have this force applied by the spring to the particle, and the direction of this force is changing continuously throughout the path, and then we need to find the projection of this force to the path to calculate the total work done by this force, and it will be a tedious process. Instead of that, what we can do is we can use this initial condition and final condition. So we can talk about the initial condition of this extension of the spring at condition A, and then the final extension at condition B. So I can write out XA, the initial extension, and XB. And then I can calculate the change in the potential energy due to the elasticity based on these two, right? And you can write out 1 over 2 K being the spring constant, x2 squared minus x1 squared. And that will be the change in the potential energy due to the elastic material here, which is the spring. Similar thing can be done for the gravitational part. Gravitational potential energy, initial condition and final condition could be written out as HA and HB, and then we can do the calculation for the change in the potential energy due to the gravitational forces. And then this part, the work done by non-conservative forces, will be about this F2 and F1 forces throughout the path. We need to do the integration throughout the path. We need to find the um, projection of these forces onto the path, and from there we can move on. Now, other than that, we can still formulate this equation, energy equation, in this way. On the left side, we have the non-conservative forces, the work done by non-conservative forces, and on the right side, what we have is the change in the kinetic energy plus the change in the potential energy in terms of gravitational and then elastic ones. Now, this is in total called the change in the total energy level of the system. So what's being said here is the work done by the non-conservative forces changes the energy level, the total energy level of the system. So we need to define the total energy in that sense. Total energy of the particle E is equal to its kinetic energy plus its potential energy due to gravitational forces and due to elastic forces. This is called the total mechanical energy of a particle. And the change in that is only possible by the non-conservative forces doing some work. If non-conservative forces don't do any work on the particle, if this is the case, then the change in the energy level is equal to 0, and then the energy is conserved. That means, so this is about conservation of energy of a particle. If there exists no non-conservative forces throughout the path of a particle, then its energy is conserved. Maybe there will be exchanges between the kinetic energy and potential energy, but then the total energy will be constant throughout the path.